Asparagine is one of the 20 amino acids that's used to make a protein within the human body. Just like every other amino acid, there's a center carbon, the chiral carbon, the stereocenter carbon, the carbon to which everything else is attached. The first thing attached is a carboxylic acid, where you've got a carbon with 2 oxygens. One of those oxygens is attached to a hydrogen. You've also got an amino group, or a nitrogen with 3 hydrogens. This nitrogen should only have 3 total attachments, so the fact that there's 3 hydrogens and then another one to carbon means there's 1 too many attachments, and this is going to carry a +1 charge. Then every amino acid also has a hydrogen that's directly attached to the chiral carbon, and then the thing that makes every amino acid different is the R group. Now, when the pH is at its lowest, when there's all kinds of extra hydrogens in the environment or in the system, this molecule is going to have all the hydrogens that it could possibly have are going to be attached. And as you increase the pH, some of these hydrogens are going to leave. The first hydrogen that's lost from any amino acid is always going to come from this carboxylic acid group directly attached to the chiral carbon, and it's going to gain back its lone pair. Now, this is going to happen at a pH of about 2.1. At this point, we've got a -1 charge here, and we've got a +1 charge here. So these are going to balance each other out. The overall molecule is going to have a 0 charge. Each has its own individual actual charge that can do something different. So if you ever have a molecule that's overall neutrally charged, but there are actual parts of the molecule that do carry a charge, this is called a zwitterion. And this asparagine is going to look like its zwitterionic form up until a pH of about 8.7, at which point the nitrogen that was carrying a +1 charge, it's going to lose its extra hydrogen, gain back its lone pair. And now this is going to be a 0 charge. This is still going to be a -1. So overall, this is going to have a -1 charge. However, the human body's pH is about 7.4, which is well below that 8.7. And so at that point, we're going to be in the zwitterionic form, where it is a negative here and a positive here, which overall makes the molecule 0 charged. Now let's talk about the R group. The R group for asparagine is known as an amide group because you've got a carbon that's double bound to an oxygen. That carbon is also going to be attached to a nitrogen that's attached to 2 other things, and that carbon is also going to be attached to another R group, in this case, another carbon. So this is considered an amide. And here you've got this oxygen where it's double bound to this carbon, and you've also got this nitrogen that has these 2 hydrogens as well as this carbon. So you've got 1, 2, 3, 4, 5 polar bonds between oxygen or nitrogen and something else, and you've got 1, 2, 3 non-polar bonds where it's carbon to carbon or carbon to hydrogen. So you've got more polar than non-polar bonds here. So overall, this is considered a polar molecule. Because there are so many polar bonds, this is also able to do hydrogen bonding with other molecules, including water, which means that this is also a hydrophilic R group. Asparagine is not an essential amino acid. You're able to make it within the body specifically from another amino acid called aspartate or aspartic acid. So you do not need to eat asparagine in order for it to show up in the human body.